still actually being answered because they can get viewers and edits. And so I'm just thinking that we'll go with the proposal first, and then the comprehensive questions can be asked, and then the other two which haven't actually come yet, then we will have to do it next week.
Okay.
Right?
Yeah,
That'll be fine. Yeah, that'll be fine. Yeah. So that's what I said. Okay, so we are going to start with Yuheng, whose proposal presentation on event analytics on social media, challenges and solutions. And the committee members are Eric Horvitz and John Crum on Skype from Redmond, and Juan Lu and Hari Sundaram in person here, and myself. Thanks.
Okay, thanks, Ralph. So today I'm going to present my work on event analytics on social media. And specifically, I will talk about what the problem is and what the challenges are and our solutions. So before I get started, I want to thank my committee members for your support and for everyone here for your time. And I hope you're not here to just enjoy the food. Yeah, there's food there, over there. So let's get started. Okay. Over 3,000 years ago, people had found a way to discuss about events. So, like this picture tells us that people came to a town hall or town square, and they chat with each other, and they discussed events of their interest. But due to the technology at the time, most of their discussions were missing. So thanks to the social media, whose emergence has created a sprawling virtual town square whose scope is big because we can talk about the various things on social media, and whose chatter right now can be recorded, can be fetched, and we can look it back. So the vast amounts of social media responses, the vast amounts of chatter opens exciting probabilities for analyzing what people actually are saying. So that is the main focus of this thesis work, which is I want to develop automated solutions to handle this vast amount of social media responses to get the insights to do in-depth analysis. So let's look at what kind of events that exist on social media. So at this end, we have very highly publicized events like the debate between Obama and Romney in 2012. And we have Super Bowl here. And to some extent, local events like the I-5 Bridge collapse is also trending, especially for the people from Seattle. So they were concerned about it, they were tweeting about it. And also we have some kind of a ridiculous event right now, just like the Obama selfie like 2 days ago, which is very kind of controversial and draw a lot of Twitter responses. For example, the tweets like this. The people said, did the president really take a sci-fi at a funeral? Right. So, given the events here, and given the vast amount of social media responses here, what kind of problems we want to explore, right? So, first, we want to know what's the relation between events and the tweets. And next, we want to know which part of the event did a Twitter messages refer to. And next, we want to infer what topics were mentioned in the event and in the tweets, and what their sentiments looks like. And also, we want to characterize, the cross-tweeting behaviors, because people are watching this debate. In the meantime, they post tweets about this debate. So we want to calculate what kind of influence of the event on the Twitter responses on its audience. So we want to calculate that. And also, sometimes, since we have a vast amount of social media, and we cannot just look at the tweets all the time to see what's going on. So we want automatically some systems tell us what's going on in the world. So in that sense, how do we detect events from social media responses? And the last, how do we predict the crowd's engagement in the future events? So given events like this, and given the tweets like this, and for a particular user, we want to predict whether this event here is of interest to this user. So we want to make the predictions. So how do we conquer these challenges, right? And what's the benefit of addressing these challenges? So there are several kind of very, very interesting applications that are enabled by the vast amounts of social media. For example, the computational journalism, as well as the political campaigns. For example, imagine for the first debate between Obama and Romney, after that is done, Obama's campaign can do a very in-depth event analysis to say, what topics people are saying about this debate, what their sentiment looks like. Probably they can derive a better strategy for the second debate, right? So the problem has attracted attentions from different industries. For example, for the news agencies, so this picture shows the so-called state-of-the-art newsroom for Fox News. So what people do here to do the event analytics on social media, so they hire this so-called event master. So his job basically is to sit here and scanning all the tweets on this big 80-inch tablet. And he basically manually look at, okay, what people are talking about and what's going on there. So far, so good. However, given the fact that we have a vast amount of social media responses, this manual coding actually is impossible. It's time-consuming. It's very expensive. So to give you an idea of how this vast amount of social media look like, so here's a plot for the tweets volume on Egypt and Morsi. And as you can see here, there are roughly around 12,000 of tweets per hour. So it is nearly impossible for a human being to look at these tweets one by one, to make sense of them, to get the insights of them. Therefore, we need automated solutions to handle this vast amount of data. So people in computer science area can look at the problems because they are always doing some kind of automated solution analysis. But the most existing solutions in this direction is primitive, meaning that people use some kind of very naive tools to look at events. For example, people have used the water clouds to visualize the people talking about. So the most frequent mentioned words are visualized as bigger, in bigger font size than the least frequent mentioned words. And this is not in-depth analysis that we want. On the other hand, you may wonder, yes, so there's an existing solution for event segmentations, right? So there's a lot of event segmentation tools. And also, there are some kind of automated tool to infer, let's say, the deep topics of the events, also on the textual documents. Why don't we just combine all those existing solutions together to handle the challenges I just mentioned before? However, I would like to argue here is that simply combining those existing solutions ignores the connections between the event and the tweets. Actually, the connection is quite complex, and I will show you later how a unified joint model can do much better than those simply combining existing solutions. So what is the problem? What is the core kind of scope of this thesis? So we want to say, given a vast amount of social media responses and the complex nature between the events and the social media responses, we want to develop automated solutions, automated tools to conduct in-depth analysis on this kind of big data. So to this end, in this proposal, I have been developed an event toolbox called Eventics to support such automation and examinations. So Eventics consists of 4 tools. So overall, it takes tweets as an input, and it focuses on 3 different core research tasks in the event analytics. So the first task I call event sense making. So by applying our tool here on top of the Twitter responses, we are able to infer the topics of the event, the segment of the event tweets alignment, as well as the event sentiments. So this can be all done in an automated way. And second, given the existing vast amount of social media responses, we want to have a way, so in the eventics, we developed a way to automatically recognize, to detect the trending events and its associated Twitter responses from a stream of noisy tweets. And the last task, what we call event engagement prediction here, essentially we have a tools to predict a user's engagement in a future events. So the event a user is not currently aware of, and we are trying to predict whether the user will be interested to get engaged with the event. So let's look at the individual, kind of give you a quick overview of the tools that I developed and how these tools can handle the challenges that I just mentioned. So let's say the first tool, which is called ETLDA, and I published at AAAI last year, I set up last year, and as well as the multimedia workshops. So what it does is it's actually a very powerful tool, and it does a lot of different things. So first, give it an event, let's say the debate, and given its Twitter responses, and given the event transcript, what ETLD can do is first, it can segment the event into a topical, very coherent chunks, where each chunk talks about a particular set of topics. And in the meantime, and concurrently, the ETLD can assign the labels to the tweets. So ETLD automatically classifies tweets into two kind of categories. Tweets can be very specific, which we call specific tweets, meaning that the topic of the tweets is strongly influenced by the topics in the event. On the other hand, the ETLD can also can give another label, which is general tweets. It can assign general tweets label to the tweets. So the general tweets here means that the event, the tweets actually is about the event, but on a very high level. For example, some people may tweet about Obama is awesome. So that is some kind of very, very general high-level tweets. So basically, the ETLD can automatically infer that. And more than that, the ETLD can also infer for the specific tweets which part or which segment of the event this specific tweet refers to. Okay? So essentially, ETLD establishes the alignment between the tweets and the events automatically. And enabled by this ETLD model, we can do an in-depth analysis. For example, we can look at how people respond to various topics in the event, as well as we can look at the event tweet alignment, how people tweet about a specific segment of the event. And last, we can visualize the evolution of specific tweets, like here. And next, given this alignment is established, we want to do more things. We want to do more in-depth analysis to make sense of events. And then particularly, we developed our second tool, which is called SockSend, published in HKI this year. So what SockSend does is, given the alignment that is already established, it tries to infer the sentiment of the topics, as well as the sentiment of the segments of the event that are reflected in the Twitter responses. For example, assuming that this tweet is referred to this segment, this tweet is talking about the topics mentioned in this segment, and this tweet is also talking about the topic of this segment. According to our sentiment analysis, people seems like they say, the topics that are boring, they don't like it. So based on their Twitter responses, we can somehow infer that the topics of this segment is boring, is bad. So basically, the SockSend can do this job. It infers the topics based on a given alignment is established. And then next, for the event recognition task, so given a vast volume of noisy tweets, so we developed another event detector called Demon, which was published in Kai this year. So trying to detect the event as well as its associated tweets from this noisy tweet stack. So what DEMA does here, to give you an idea, is to identify a trending event, where the trending event consists of trending features like the words and unigrams mentioned here. And also DEMA can infer the time point where the trend starts. For example, the DEMA, given the tweet, assuming tweet here, the DEMA can infer there's a fire happening at the 5th Street and Pike. And sirens are heard and lots of smoke at a certain time point. So the last tool is called Alice, which is under review right now. It's for the event engagement prediction. So what it does is, given an event like this, and given the people's engagement that are already in the event, and given a person's past event engagement, the Alice is trying to make a prediction, trying to generate a kind of a message like this. Say, hey Mike, we find that this event might be of interest to you based on our predictions, where our predictions is made based on your past engagement and maybe your friends that are already involved in the event. So based on our prediction, we find, yeah, you might be of interest in looking at the event. So essentially, the Alice, although we call it event engagement prediction, essentially what it does is somehow it is some kind of event recommendation engines to recommend potential interesting events to the potential users where the user is currently not aware of this event. So here is the summary of the contributions that I have made under these directions. So we developed the toolbox Eventix, which is a fully automated toolbox, and it can conduct in-depth analysis of 3 core research problems. So ETLD and SOCSAT for event sense making, DEMA for event recognition, and Alice for event engagement predictions. And enabled by our toolbox, we also made a lot of some kind of interesting observations on how people respond to the event and what factors that affect people's engagement. So our research in this direction somehow attract media's attention, like Seattle Times and different local news as well as the social media attentions. And also the DEMA work won best paper honorable mentions at CHI this year. So it seems like people like it. Okay, so next let's talk about our tools in more detail. And given time constraints, I want to emphasize that I will mostly talk about SOCSAT, the ETLD, and SOCSAT for the event sense making test. And I will only briefly review, quickly review the DEMA and Alice for the event recognition and event engagement prediction test. But I'm happy to take any questions about it. Okay, so for event sense making. So given the event like this, the debate, given all the tweets that about the debate, what do we want to do? We want to infer what the relation between the event and tweets, right? Also, we want to know which part of the event that this tweet refers to. Besides, we want to know what were the topics mentioned in the event and in the tweet. And the last, want to measure the influence of the event on Twitter responses. So here is the problem definition for the task that this ETLD is going to do. Is given an event transcript S and its Twitter responses T, we want to characterize the event in terms of its topics, the segments, and its influence on the audience tweeting behavior, how we can characterize that influence. So basically, this requires that we need first extract topics from the events and from the tweets. And also, we need to establish the alignment between the event and tweets. And next, we need to segment the event into topically related segments. And last, we need a way to capture, to model, to characterize the influence of the event on its Twitter responses. So you may wonder, yes, that sounds very interesting problems. And do people look at a problem before? The answer is yes. And I will talk about this in the next slide. But before that, I want to mention the challenges we have. So the most challenging part here is the topics and the segments are latent. So they are not on the table that's ready for us to look at it. So they are latent. We need a way to uncover this kind of latent informations. And then also tweets, right? When we talk about tweets, since tweets are in response to the events. So the tweets actually are topically influenced by the content of the event. And the topics of tweets can be two types. It can be very general, meaning that it is weakly influenced by the events, by the content of the event, and it's constant across the whole event. Or it can be very specific, meaning that it is strongly influenced by the event. It's pretty episodic, and also it's probably related to a specific topics or specific segments that mentioned in the event. And last, the event is formed by a discrete, sequentially ordered segments, where each of which segment talks about a particular set of topics, where the topics is latent. So how do we overcome these challenges? Next, let's look at the possible solutions. Yes.
Before you go ahead, I was waiting for this clean definition. What do you mean by an event?
Oh, so the event. Let's see. That's a good question. So definition of event actually is very hard, and people are trying to debate what the event really is.
But you need to have a definition
yes.
of an event to detect it, right?
Yes, I do have that. Let's give you slide. Oops. Maybe it's not showing here. Okay, so I talked about the. I thought I made the background slides, but so let's first go back to here.
I only asked because I couldn't find it in your slides.
Oh, yes. So the definition of event is as follows, especially in the Twitter space. So the event is a occurrence. So I try to give the definition of event in the Twitter space because there's a lot of different definitions, and I don't want to reinvent the wheels here. So the event in Twitter is defined as event is occurrence, and it occurs at a certain time point t, and it's associated with a bunch of messages, Twitter messages M. So given this definition,
but what is this got to do with I thought your key aspect of event sense making is you're connecting real world events with tweets, right? So
here the scope of the event sense making is that we look at the events in Twitter. So let's say.
But how will it have a transcript?
We will say, so this is the limitation of the tool here. So as we see this tool, the ETLDA, as well as the tool that we present later, the SOCSAN, they relied on the textual kind of projections of the event, which is the transcript. And
you gave a lot of interesting examples, really interesting examples. One is the events in Egypt,
yeah.
Macy's Thanksgiving Parade, and you gave Romney's debate, right?
Right.
These are all very different kinds of events.
Yes.
Right?
Yep.
So, but if you're claiming that you want to characterize all of these events through analysis of tweets, how is this going to work? You need to have a clean definition.
Oh.
What is a real world event that you're planning to analyze whose projection that you're seeing on Twitter?
Right. So that's a good question. So the event, as I said, here is the event I started here is plan events with textual projections, which is the event transcript. So the planned events, meaning that the event is planned to occur, so we know it in advance, and it has other information for us to get the event, which is the hashtags or the topics. So we know this event, like the debate, it will going to happen at a certain time point. And also, we know that it has textual projections. The transcript will be available at New York Times. So
does the event, so you can't therefore characterize a protest?
Oh, yes. So that will be in my proposed work. So that I will mention later on.
So any spontaneous event that doesn't have a transcript cannot be analyzed by your system?
So that's also in my proposal is how can we develop a way to do the online event analysis rather than have everything, have the transcript available already, full kind of transcript available, full set of tweets are available. And so essentially, so the limitation of ETLD, the model that I have already developed, is that it has to wait until everything is ready. The transcript is ready, the full part of the transcript is ready, the full set of tweets is ready. It does the kind of after effect analysis.
No, the problem that I'm having with this is that you don't have a clean definition of what is actually happening in the physical world. So the debate, okay, seems like a simple, well-defined event, but it's happening at a particular location at a particular time,
Right.
and it's finite in both time and space.
Right.
But something like a New Year's Eve, say, celebration, which happens all over the world,
Right.
is not temporally, synchronous or spatially co-located.
Right.
Right. But you're not having a formal understanding of what real-world events look like, whose projections that you want to see. I mean, that's the struggle that I'm having with this, because you're starting with the debate. It seems, okay, of course events are like that. We have a transcript. Events are not generally like that.
Right.
Events are not only those that happen on TV.
Right.
Right?
Yes.
You don't say.
I'm sorry?
You don't say. I mean,
I mentioned in my proposal, not here, is I give you some kind of characterizations of the event, and so we actually the whole the toolbox works on kind of two events with different dimensions. So essentially, the tool, which you can see as a kind of limitation, is it only works on the planned events with textual projection that is available. So I admit it is the kind of limitation of the tool. It cannot handle, the toolbox cannot handle all the events that, like you said, a Christmas Eve or celebration of that. It cannot handle, so far the tool, the ETLD, cannot handle these events like that. But it does very well for a specific kind of type of event, which is a plan, and it has textual projections. So it works specifically on that. And my other tools, like the DEMA, the event detection tool, essentially handles events that is trending. So
will it work on Macy's Thanksgiving Parade, which is a planned event that takes place at a particular time?
Oh, so that event is not considered here. That will be considered in my proposal.
Why? It's consistent with this idea, right?
So
it will have a transcript, it will have tweets.
Oh, you mean that? Yes, we can directly apply the ETLD models to that, for sure. Once we get, let's say, New York Times article on this.
No, you have the transcript of the commentators.
Oh yeah, that's true. Yeah, ETLD the models can handle that situation, that type of events. But we didn't do the experiment, given the time of the paper that was published.
Okay.
Yeah.
All right.
Yeah. But you will see later how I do notice this kind of limitation that the scope of ETLD and SoftSend is limited by the type of event that it can handle right now. But in my proposal, as I mentioned, how I can go beyond to handle much more type of events. Okay, so I'll mention that later. Okay, so challenges. So possible solutions for this event sense making task for these planned events like the debate. We can first apply existing event segmentation tools, such as time window-based segmentation tools first to get the event segmentation done, and next after the segmentation, for each tweet segment pair, we can measure their closeness, their similarities. So by some tools like some schemes like TIFF-IDF, we can measure their similarities. And if the similarity is above certain threshold, then we will say, oh, this tweet is referred to this segment. So that somehow established the alignment between the event and the tweets. And next, to characterize inference of the event on its tweet responses, we basically can do a counting, right? For each segment that we get all the tweets that refer to this segment, and then we can count the number of tweets. So in that way, we can somehow infer what kind of inference that this segment generates. However, this approach has certain limitations. So the first limitation is that they are not able to discover the latent, topics, latent segments that we want. And also, the second problem of this approach is they model the events and the tweets independently. So they ignore the connections between the event and the tweets. So as we will see later, how our tool, the ETLDA, can perform much better than these tools, because ETLDA basically models the events and the tweets jointly. Yes?
What is the utility in studying tweets if you have the narrative of the entire event?
Can I say that?
If you have a narrative of the entire event, so that means you know what the event was about and what was involved in the event. So why would you want to study tweets which is not the end?
Oh, so that's a good question. So why do we want to look at the social media responses to? So is that your question? Why do we look at since the event transcript is available? Why do we look at the people's responses? Yes. So the thing is that events, the people can pick the certain topics of the event that they will talk about it. So the view reflected in the tweets does not necessarily equals to the view that reflected in the event transcript. I mean, it reflected in the event. So it's much more kind of personal. They have much more personal opinions. So after we establish some kind of alignment, so somehow we can establish alignment based on their topics. We can learn what people actually are talking about. Given that the topic in the event is about healthcare, right? What other related topic and personal kind of conversations around this healthcare topic, and what kind of sentiment that reflected about on Twitter in response to these topics, healthcare topics. So without these, without the social media here, if we only look at the the transcripts of the event, that's more like traditional kind of journalism. They look at the facts. But right now they want more kind of contextual information about, yes, what other people are talking about this event, right? Not only what Obama and Romney said, what other people are talking about. So that can give you a better kind of event experience. Did that answer your question?
Yeah, why segments are latent? Yeah, I understand the topic are latent. Why segments are latent?
Oh yes, that's a good question. So they have on the event transcript. So naturally, the paragraph can be seen as a kind of segmentations, right?
Yeah.
The kind of initial segmentation of the event transcript. But the thing is that, especially for certain type of events, for certain type of transcript, different paragraphs can talk about the same topics. And I will show you later how we can derive some kind of a smart way to combine all the paragraphs that talk about the same event. Talk about the same topic into one segment. So segment consists of at least one paragraph. So one segment can actually it's a latent kind of box. You can see can we apply on the event transcript. So one segment can have multiple paragraphs. Can have and where these multiple paragraphs talk about one single kind of concrete topic.
Then how many latent topics or segments we need?
Oh, so that's so I will show you later. So basically, there's a parameter that controls kind of what's the kind of that gives in advance to say how many topics we want to cover, and the model automatically will determine how many segments we have based on the topic distributions. Okay, so far so good, right? Okay, so now we talk about our contributions to the ETLDA model. So the ETLDA is a hierarchical, fully Bayesian model. It belongs to the LDA, the topic model family. So it's a fully Bayesian model, and it jointly models the event and its Twitter responses based on their interdependency, which we call topical inference here. So here is a conceptual model for the ETLDA, where we have the event transcript, the textual projections, and we have the segments here. Each segment consists of several paragraphs, and each segment talk about a particular set of topics. And we have two types of tweets. Tweets can be general, like these blue ones. They talk about a very high-level kind of topics about this event, and it's constant, like Obama is awesome, like something like that. And on the other hand, tweets can be very specific. it may refer to a specific topic mentioned in a particular segment. So ETLDA can automatically infer among these three segments which segment this tweet refers to. So in an automated way. So since the ETLDA is a Bayesian, fully Bayesian model, so let's talk about the generative process here. Okay? Before going to the technical details later. So the generative process here is that for each paragraph S belongs to the where big S is the transcript. So we first draw a segment choice indicator C of X. It's a binary variable. So if C of S equals to 1, then we draw a topic mixture for S. Otherwise, if C of S equals to 0, then the topic of S is the same as the topic of its previous paragraph, S minus 1. So to answer your questions, so we basically have this step to answer your questions. So which means that if S, the topic mixture of S and topic mixture of S minus 1 is the same, then we basically merge them together into one segment.
Yeah, I knew some work in this talk. They use this sentence as a unit. They don't use this paragraph as a unit.
So in the experiment, we use the sentence. We're not using the paragraph. So for the tweets part, yes.
So what if I talk about topic X and switch to Y, then again to X?
Right. So that will be three segments. X is itself is segment, Y is segment, and X is segment. So if you talk about X, X, Y, then you will have two segments. X, big X segment, and Y segment. Yeah. Okay. So for the tweets part, okay. So again, we have a binary kind of variable to determine what type of tweet this tweet really is, either general or specific. So we have a binary changing indicator C of t. So if Ct equals to 1, then we draw a new topic. So Ct equals to 1 meaning that this tweet is a general tweet. So we draw a general topic for this tweet. If Ct equals to 0, meaning that this tweet actually is a specific tweet. And based on our definition, the specific tweet is the one that refers to a specific segment. In this case, we first draw a paragraph S, which is, in this case, the paragraph S, the topic is the same as the segment that this S belongs to.
So
yeah.
So this topic and segment assignment is a hardware or a software. The things is hardware.
Which one?
I mean the assignment draw.
Oh, here.
Yes.
It's a software. Basically, we basically based on the distributions, we have a probability. Say we have 5 segments, and the segment 1 can have like 0.8 probability, and then segment 2 is like a 0.2.
So basically, CS and CT are to determine whether we draw a new topic or not. But the probability of this and the segment and this paragraph and the cases depend on some distributions.
Yeah, I will discuss later. This is kind of generative process. In next slide, I'll talk about what's the distributions behind this. So as I said, so for the specific tweets, we first need to draw a paragraph that this tweet refers to from some distributions. Then we assign the topic mixture of this paragraph. We assign the topic mixture to the tweets. So essentially, the segment or the topic of a specific tweet is the same as the topic of the segment that this tweet refers to. So this is a graphic model for the ETLDA. Okay, and if you are familiar with the LDA literature, essentially this and these are kind of too big the LDA, the topic model, latent distribution applications, where they are connected by various latent variables. So in this part, it's a plate model to characterize the generative process of the event. And in this part, it is a plate model to characterize the generative process of tweets. So we have this, for the events, we have this a binary variable C of t to determine the segment. So since it is a binary variable, it is sampled from a Bernoulli distribution to automatically say, to sample the probability, right? And depending on the result of here, we have this variable theta to determine the subtopics of each segment. So, as mentioned in the last slide, it has two choices. It can either sample from a new topic, which is from the literature, or it can sample from the topics of S-1 for the segment for the parallel S. In that case, we use the delta function to calculate to modify this kind of the same topic, share the same topics. And also, depending on the topic of theta, we have this topic indicator Z to sample, to take theta as the parameter, and then we sample the topics in a multinomial distribution. And then, on the other hand, for the tweets, we have this the tweet indicator C of t. So since it is the binary variable again, so we sample it from abnormal distributions, right? So if a tweet is a general tweet, then we need to determine which segment this tweet is refers to. That goes to this variable st. So st sampled from a categorical data distribution. What it does, it's given all the segments that are made here. It's pick one out of these segments. On the other side, if the tweet is a general tweet, then we have this variable. So basically, general tweet is sampled from a general topic, which goes to here, this side, which is sampled from a Dirichlet distribution to generate the topics. So given these different choice that will affect the topic distributions for Z, which later affect the topic of this word W. Yes.
So am I correct in understanding that time is not really part of the model, so that you could mix up the order and the tweets and it would all be the same?
That's a good point, and we will see later. So I will go back to your what you asked later. So yes, so time sensitive. Time is not a sensitive kind of time is not a kind of variable here. So this model is not sensitive to the timeline of the event. So and that actually enables a very interesting observations that I will discuss later.
You could tweet about a future event.
Yeah. Well, it gives. Okay, I'll talk about that later.
Okay.
So just go back. So LDA is very well understood.
Yeah.
Segmentation of transcripts is a very old problem.
Yeah.
What is your contribution here?
Oh, so the whole contribution is that we have a. So we have we developed this joint model to model the events, the generation, the events and the connection between the event and the tweets.
So you're saying your contribution is data and feed? Is that your contribution? Because essentially what you're saying is that the connection between the two different temporal sequences is your contribution.
So in terms of the models, it extends the LDA by considering the whole kind of topic inference between the tweets and the events, which you cannot easily do if you just apply the traditional LDA models, right? And so basically we have a new way to model. We look at events and tweets, we look at them and we put them in a very unified framework. So at one time, we're trying to model what the event is going to generate. And the other time.
So let me ask you this.
Yeah.
Do the topic allocations, what is the connection between the topic allocations on the left with the topic allocations on the right?
Okay. Yeah.
What is your innovation here?
Oh, so basically the first innovation that actually we have this, if we talk about just the models. So first innovation here is we have a generative process for the event segments that I never kind of talk about before. The second innovation in terms of the model here is that we model different type of tweets. So to answer your question is what's the topic, how topics of this part influence this topic, the topics of this part. So basically that depends on the variables that's here. So as I said in the generative process, so if the tweet is a specific tweet, okay? If a tweet is a specific tweet, it can talk about a very specific topics that mentioned in a specific segment, right? So in that case, how do we draw the topic distribution for these tweets? So these tweets, the topic distribution is as same as the segment that this tweet refers to. So assuming that this tweet is talk about healthcare, that Obama running debating about healthcare in the event transcript. So they have a big paragraph about.
But that's basically just the topic, right?
But that's topic distribution. Yeah, you're right. That's what I mean. Oh, so then if we can automatically infer, so basically if we can automatically infer that okay, this tweet is talking about this part of the event, then we can establish the alignment between the tweets and the event, right? We can somehow know okay, what this tweet is talking about, and which part of the event this tweet is talking about, right? As you may wonder, yes, we can apply the LDA on the topic. On the events, right? We can apply the LDA on the tweets. Then basically we can measure their distance by the different divergence, KL divergence, JS divergence. That's our baseline actually in the experiment. So I will show you later. So how this kind of unified joint model outperformed this kind of.
But the idea of coupling across different temporal sequences, are you saying this is the first work that actually studies coupling? So you're not aware of coupling between two different temporal sequences? The idea of alignment between two temporal sequences?
I mean, in terms of this generative model, I'm not aware of that model's two kind of. There's a lot of kind of joint models for different. Let's say for different
temporal sequences.
Because the tweets here, we basically define a different type of tweets, right? So that's why we developed our own kind of graphic models here. So did that answer your question?
To some extent. Okay, maybe we'll come back to this. I don't want to stop you.
Okay. So the inference in the ETLDA. So since ETLDA belongs to the LDA family, right? And LDA family, the model there are well known that the inference is intractable. And therefore, we need kind of approximate algorithms here. The one we pick here is sampling. So basically, we want to infer this conditional, this posterior. We want to know this sorry, this is a typo here. So basically, we want to know Z of S, the T, C of S, CT, and ST, given the two observed variables, WS, WT, where WS, WT is the words mentioned in the transcript, and the words mentioned in the tweet. So S represents the signal, and T means tweet. So, since it is hard to infer this, we use keep sampling. And what keep sampling does is it approximates the posterior distribution by iteratively updating the parameters, the variable here, given the remaining variable. And here is some kind of result after the updating equations here. So to evaluate the LDA, okay, we have three tasks. We want to evaluate the event segmentations. We want to evaluate the topic extractions. Also, we want to evaluate the alignment between the events and tweets. And to set up the experiment, we have two sets of data. The Obama speech on the Middle East use the hashtag Emmy speech. Since it is a planned event, we know what hashtag looks like, right? So it's official, like White House hashtag Emmy speech. And for the second data set, we use the Reagan debate. And we obtain the transcript, the textual projections from New York Times. And then we train the models. And to test our model, we have two sets of baselines. So the first baseline is the original LDA model. And second, to test the segmentations, we use LCSEC, which is HMM based.
So why is your assumption that anything that is tagged with this is the only set of tweets relevant to the debate? Isn't that a strong assumption?
Can I say it?
Why is the tag, first of all, I'm asking about...
You mean the hashtag?
I'm asking about the sampling problem of sampling from Twitter. You're assuming that your sampling methodology is that, only those tweets that have this tag, that hashtag, are relevant. How good is that assumption?
Oh, well, that's a good question. So basically, what do we want? So when we collect the tweets, because the hashtags are known in advance, so we basically set up our crawlers to get the tweets. So if we use different ways, let's say we use keyword search, right? We get a tweet by keywords.
then the problem is that will give us kind of some kind of noise. So, and we need to determine what is the right keywords we need to set up the product. So if we search Obama, Obama is pretty mentioned everywhere at any time. So the tweets, if we use Obama as our search keywords, the tweet that we generate will fetch is not only about the Emmy speech at that time, but also about say Obama is also Obama is Obama today wear a nice suit, and Obama, I don't like your healthcare policy, and something like that.
So I think there are two different questions. Is the problem to identify all relevant tweets difficult? Yes. But that doesn't mean that you take the simplest possible approach, saying that I will only use this particular tag. I mean, to me that seems like a limitation of your conception of how do you sample for tweets for this particular tag. And the second thing I want to ask in relation to the sampling again, do you have all tweets that were ever published with this hashtag?
Oh, so basically, so to set up this experiment, what we do actually here is, I remember this was published in last year. What I remember is we set up the crawlers like 2 days before the actual event that is already happened, and we close the connection and we close our crawlers like 2 days after the event has happened. So we do have a data that tag those hashtags before the event, during the event, and after.
Did you crawl with a whitelisted server?
Oh, well,
a firehose?
We don't have that ability. We only use this. We basically use the streaming API.
The standard API?
The streaming API. Yes.
So how do you know you have access to all the tweets then?
So unfortunately, there's no other ways we can do to get these tweets. So that's definitely a limitation. If we have, let's say, access to the firehouse, probably we might generate a different results. That's also possible. And but that access we don't have it, so we have to go with what we have. Right?
No, I completely understand this, but I'm saying you must also recognize the methodological limitations. If you have a sampling problem, if you don't have access to the right data, your inferences cannot be maybe significant. I mean, yes.
I'm just trying to understand it. So your point is that if you were to make insights about the public event based just on the sample tweets, that may be not fully covering what
that's
you
right,
said.
that's right.
But the technique itself, you have good questions, right? Okay, because it's currently just evaluating the technique with respect to any sample of tweets.
So the question is, what is the significance of the result that he's getting?
Well, there are two different kinds of results. One is just evaluation results, other is inferences.
Absolutely. Yeah.
So to answer, so I'll go back to your point later. So the first results on the event segmentation. So here are the results that done by the ETLDA. So each bar represents the event boundary, and we basically measure the performance of ETLDA against the LC-SEC, and which is here. So the ETLDA performance better than LC-SEC in terms of the PK value. So the lower the better. So the PK value is the probability that a pair of words that's from the event is wrongly segmented. So next, so the topic distribution.
How did you get the ground truth for the event segmentation?
Oh, so we have a manual annotator.
Did you do it?
Oh no.
Okay. So where did you get it from?
So basically.
Okay.
No, not these people. Actually, this is the work that I've done in Biolabs. So we have other people not part of the project, and
there is ground truth that is cross. Okay, that's what I wanted to know. That's all.
Okay. And if you want the agreement between each other, that paper also says what's the agreement between the annotators. So these are the topic extractions. Yes.
So I have a question about the segmentation.
Yeah.
So this is independent of the tweets, right? It's just based on the transcript?
Oh, no. So basically, so the ETLD model can do the segmentations as well as the classification of tweets in one time. So given the event transcript, given the tweet that as the input, and let's say this ETLD is the black box, it will give you the segmentation boundaries here because
When you
it's a
showed your generative model, it was kind of it looked like I had the impression that it was only kind of learning things based on the transcript, and that was like looking the tweets.
Oh,
Not
so
doing the
so
other
no. So somehow we find that. So to make the essentially the event segmentation is dependent on this variable CSS, right?
Okay, I think I see now. I missed the error
Yeah,
there.
yeah, because if you go to the details of the inference, I mean the updating equations, keep sampling updating equations of for this variable, you will find that some inference about from the tweets is also mentioned there. Okay, so these are the topics, and we again measure the quality of topics against the LDA. Basically, we apply the LDA on the transcript of the event, and we apply the LDA on the tweets, and then we again invite people to evaluate manually. And this is a normalized per scale. And we can see ETLD when outperform the LDA models. So
What is S1, S2, S3?
Oh, S1, these are segments.
Are these differences statistically significant? Was 0.51 statistically significant from 0.48?
So I just show you as three of them. But we have because I cannot make a longer table.
No, are these differences significant? Yes.
Oh yes.
Statistically significant.
Yeah, we mentioned that in the paper. Yeah. And also this result is also statistically significant. Okay, we mentioned that in the paper. So here is the result on alignment. Event tweet alignment. So what we want to do essentially is we want to infer whether a specific tweet is correctly identified by a specific segment. So for ETLDA, that task is quite straightforward because ETLDA is designed for that. But for the LDA, we have to develop our own ways. So what we do here is we first, to establish the baseline, we first apply the LCSEC to get the event segments. And then we apply the LDA, the topic models, on the segments of the event that get generated by the LCSEC. And then we apply the LDA on the tweet. And we measure their topic similarities between these segments and the topics, and the topics of the tweets. And we establish somehow this kind of alignment. And we give the user, say, do you think the reference, the alignment of the tweets to this segment that makes sense to you? So again, this is the results. Okay, so enable X. Yeah.
So do you want to be close to the actual transcript? Because I think you mentioned that you expect the tweets to show some sort of different opinion. If you want to be actually as close as the actual transcript,
right?
Not just the transcript.
Oh, so basically, we want to infer the latent topic distributions on the tweets. So yes, some tweets may contain the words, say, their own opinions, but their latent topic distributions may probably about, let's say, the latent topic distribution is about healthcare, and they mention that in their tweets, but they also add a word. They also add their own words about this healthcare. So we are hoping that it is our hope that the LDA can actually cover that. To explore.
I'm just saying that since you're using JS, which is like kind of normalized KL,
yeah.
the thing is that they only match when there is an overlap in the topics.
Right.
So if there's no overlap, your JS would be 0.
Well, so basically here, I'm not saying every tweet that refers to this segment, right? So it's possible that it's 0 because it is kind of, we basically have some kind of threshold here to eliminate the kind of lower score on the GSM. Okay. Yeah.
So what's the highest performance of this? What's the highest performance? 1, right? If
Oh no. So basically this is a Likert scale.
So what's
1
the
to
high?
1 to 5, and we normalize that. Yes, it's 1.
It's 1, right?
Yeah.
So you said that you will have the following tasks based on this task. So I don't think this performance is very good. So how you
What do
make
you
sure
mean
that
by-
you mean you will use this alignment to do this sentiment analysis, right?
Oh, that we mention later.
Yeah, but this performance is what very good. So how
Oh,
do you make
no,
sure?
that's not the performance. Basically, this performance are the score that human gave. It's not the performance that actually, the thing is that we don't have a ground truth here, so we have relied on humans to give our ground truth. We don't have a ground truth.
So I mean the performance of this alignment will, your following tasks will be very sensitive
yeah.
to the performance of this alignment.
Yes.
So I want to know how good these results are.
Oh well, so.
But basically, if the scale is 1 to 0,
right.
or 1 to 0 to 1, the performance is very good. So how do you make sure your following tasks?
So basically, I want to say here is, so first the value here is normalized, and it's like a scale 1 to 5. It's subjective.
Okay.
5 is the best, 1 is the worst. So it's subject. It's subject, and because we don't have a ground truth, we ask humans to give our labels. And also, in the next task, we will see later, actually if we apply the LDA here, basically the ETLDA, since we demonstrate that its performance outperforms the LDA, so this is a better choice than the LDA that we were going to use.
I see. I hope you have.
1 second. Because in the interest of time, thank you guys for all your interest, but in the interest of time, Hari was asking me that we should speed up a little bit. So, please, if there are questions that are that can be taken after the talk, please do that because I think we have too many topics to cover. Also, you need to go faster on the SOC sync because I don't think if you are going at the rate at which you are going, we'll basically not have the time.
Okay. Because we need to, the whole thing needs to finish by 11:30, including the deliberations. So.
Yeah. Oh, okay. So here, I will skip this. And then I'll skip this, probably, and go to the, I'll come back to this later when we talk about the success. And so skip this, so I will go ahead to talk about the proposed work. Somehow that, hopefully this answer address some of the concerns you have. So, so here, we want to know, so LDA seems powerful, right? But there are remaining questions, especially what's the robustness of the ETLD? How ETLD can handle incomplete data, right? The next is the predictive power of ETLD. So how it can predict what's going on in the next given when we have seen here. There are possible solutions that I want to investigate in my proposed work. We want to investigate different inference algorithms first to see whether they can do a better job when data is incomplete. And next, we want to first train for the predictive power of ETLDA. We want to first train it on a training data set, and then we test it. So what's the outcome for this? So the outcome is that we want to actually do an online analysis of events rather than after the effect analysis. Because in many cases, after the effect analysis is not as valuable as the online effect. Because the journalist probably has done all sorts of after the effect analysis. So we can do better, say, in the middle of the event. We want to do in-depth analysis. So after the alignment is established, what we can do? What other tasks we can do based on this alignment? So here, we want to infer for each segment here, and for the topics mentioned here, we want to infer the sentiment of the topics, of the event topics, the sentiment of the tweets, the sentiment of the event segments that are reflected here in the tweets based on the alignment. So the problem here that we'll try to address is given event transcript S, and given associated tweets T, and we want to find aggregated sentiments on the event topics, event segments that reflected completely. So sentiment analysis is a very well-studied area in past few years, and there's a lot of solutions that are available. Probably one may imagine that we can directly apply this to our problem to address the challenges here. So how do we do that for the existing work? So the first is we can manually label the tweets. We can generate some kind of training set. And we can apply some existing tools, the classifier, such as Minka, to learn the sentiment orientations. And then we can relate the aggregated tweet sentiment to the event topics, to the event segments that occur within a fixed time windows around the events. But is it sufficient? Unfortunately, it's not. So here are the challenges that makes this existing work not fit. So the first is it's difficult to relate the Twitter sentiment to the segments and topics of the event. And actually, since I skipped, but I want to mention a little bit here is that the fixed time window approach somehow is not valid in certain times. And also, manual annotating sentiment of a vast amount of Twitter is time-consuming and error-prone, which prevent learning a good quality model. And the last is the sentiment of Twitter is pretty contextual. It's pretty dynamic, right? So people can invent a very different slams and use in the tweet that cannot be captured by other models just for this event. And for next event, they use different slams. So, which will cause the model to lose performance if we cannot capture this dynamics. So how do we overcome these challenges? So we developed our own solution called SockSent. So basically, SockSent is a matrix factorization framework. It leverages 3 types of prior knowledge to overcome the challenges that I mentioned in previous slides. So ETLD basically first align tweets and the events to overcome the first challenge, the limitation of the time windows approach. And second, it has a sentiment lexicon to overcome the challenges, the third challenge. So we can basically add our own kind of slam. We can basically design our own kind of sentiment lexicon, which add the customized sentiment orientation on slams. And next, we only need to improve the performance of the model. We require a small set of labels. And so the SockSent framework incorporates these 3 prior knowledge into one unified matrix factorization framework. And it learns factors along 3 latent dimensions: the topic, the segment, and the sentiment. So this is the model for SockSent. So given an input tweet terms matrix, we want to learn, or we want to factorize it into 4 factors. The tweet segment topic, topic sentiment, and turn sentiment, right? And we want the learning process as good as possible. Therefore, we apply the prior knowledge here to enforce the learning process. So the prior knowledge, the first prior knowledge is from ETLDA, which is the tweet segment alignment prior knowledge. That's a matrix form, a matrix form. And next is the turn sentiment matrix from the sentiment lexicon. And the middle one is the tweet sentiment matrix to regulate the production of these 3 matrices. So we model the whole learning process in one optimization framework. So basically what we want to do here is we want to minimize the learning errors, the factorization errors here. So the X is the input tweet term matrix, and GT and SF are the factors that we want to factorize out. And to regulate the learning process, we enforce the 3 types of prior knowledge, F0, R0, and G0 here. And one good thing of this framework is that it can give us a different combination. As a result of these factorizations, we can basically manipulate the factors to some extent to answer the questions that we want to answer, we want to address. Let's say T times S, T matrix times S matrix can give us the segment sentiment matrix. The production can give us this. And G times T times S can give us the tweet sentiment matrix. And S itself is the topic sentiment matrix. So by different combinations, we can get what we want. So this is how this prior knowledge looks like. So I want to highlight this G0, the prior knowledge from, okay. Here, it's the distribution, it's the alignment result from ETLD. And here are the learning process for the SockSent. So to evaluate the SockSent, we have 3 tasks. We want to learn the sentiment quality for event segment. We want to learn the topics, we want to also evaluate the effectiveness of the prior knowledge. So you can see here we have different baselines, and as you can see here, the yellow bar represents the performance of Soxent. So Soxent, since it utilizes or leverages the partially available prior knowledge, it performs much better, and with improvement from 7% to 80%. And also, this is the effectiveness of the prior knowledge. So here, we make different combination of the prior knowledge, and we want to see what their performance, how definition combinations give us different performance. So the point I want to make here is the domain-specific knowledge here is particularly helpful in its corresponding task. What that mean is, let's look at the first column, which is about the sentiment performance on the segments. And we can see here all the prior knowledge that contains this prior knowledge, this G0, where G0 is the event tweet alignment result. Performance is much better than the combination just without this G0. Which means that the G0 basically enforces a lot of good prior knowledge that helps to improve the performance in its corresponding task. So to answer the other concern you have is, are ETLDA and Soxent enough? The answer, of course, is we know there's limitations. It's not, because the ETLDA and Soxent heavily rely on the textual projections, right? Which is the transcript. So what if the transcript are not available? Right? What can we do there? Then the problem is, if we want to follow the solutions we have for the ETLDA for the Soxent, the problem is, how do we establish the kind of virtual alignment between the event and the tweets? Why event this textual projections, the event transcript is not available? How do we do that? So here are the possible solutions, right? So we want to, in my proposal, we want to explore the solutions that can do automatic event segmentations just based on the tweets. We want to see how we can automatically split the entire tweets that in response to the event into different segments, where each segment talks about a particular set of the topics. And there are a lot of work to model how the topic transits from one topic to another, and we want to incorporate that. And furthermore, also we were wondering, so there are some kind of other signals probably we can leverage to model the stage transition in the event. For example, it is possible that at one stage, between one stage of the event and another stage of the event, maybe there are some kind of emotion change, maybe some linguistic change. Probably we can use that as a kind of background knowledge, and we can incorporate both this event knowledge here in one unified framework to model both the topic transitions as well as the event stage transitions in one unified framework. But what's the outcome here? So the outcome is obvious, is that we can gain a deeper insight. We can make the event sense making work just based on the work, based on the tools that, and where these tools do not require the textual projections. Okay, so I can quickly go through the other tools that I have. So we want to know how do we detect events from social media responses as our second test, the event recognition test. So essentially, what we want to do for the problems is that we want to find the event where it consists of several topically related trending features, where features is a unigram, it's a term, right? And we want to know that at a given time, where trending is the time interval where the rate of changes is positive. So there's other definitions of this trending here in the literature. For example, the volume of tweets or volume of a word, frequency of a word, is way beyond the expected value. Then that's trending. So here we adopt some kind of physical meanings based on the momentums. So here are some challenges. So we want the solutions as general as possible. And the most important point, the requirement is that we want to locate when the trend starts. So existing solutions, so there have been recently there have been existing research work on how to detect events from the social media. But all they can do is that they can only tell you at time X whether there is a trending or not. However, they cannot tell you that if a trending X when it starts. Why is it starting? It cannot tell you that. So we want to basically answer that question. And the last is we want to differentiate the detected events, whether it is trivial or not. For example, if we can detect, say, good morning everyone, that could be some kind of topic or trending topics. But that is boring because it's a repeat every day. So we don't want that. We want some more novel ones. So that's our third requirement. So here, our contributions, which we call DIVA, published in Kai this year, is that DIVA has an unsupervised event detectors, which takes 3 steps. So first is we identify the trending features. And next, we rank the trending features based on their novelties, based on how they're different from their expected values, how they're normalized by their standard deviations. And last, we want to group those trending features. Because in our problem definition, we want the topically related event is an event that consists of topically related terms. So basically, we want to use this step to group all the topically related terms in the classroom. So here are the sample of detected events, and here are the trending terms that we detected to represent the events, and here are my labels I gave manually, and here is also the type of trending identified. Okay, so the last one, which is how do we predict the cross engagement in the future events? So give a tweet like here, and give an event like here, and for Mike, we want to predict whether Mike is interested in this event. Is likely to get engaged in the event. By engagement here on Twitter, I define that as a set of actions. A post, reply to, or retweet a tweet about this event. So that's the way I define engagement. You may have different way to define engagement, but this is we optimize engagement here into the Twitter space. So basically, then the problem is how do we categorize this engagement, right? And how do we find the factors on Twitter that can affect, that potentially affect the engagement? So inspired by the work in consumer engagement, right? So the people there in marketing, they have like this kind of conceptual model to define what elements in the engagement. So what they call it is you have involvement, they have intimacy, interest, influence, and interactions. Then we took that kind of conceptual idea, and then we applied to the Twitter space, say, based on some kind of definition of involvement, what kind of feature, what kind of factors on Twitter that represent this involvement. So at this end, to this end, for the involvement, actually, we find the features like the number of tweets that this guy posts, the number of tweets per hours, the highest tweet that a user posts per hour. And for the intimacy, what's the mood, what's the emotions that are reflected in the tweet? For example, how many messages this user tweet about certain event engaged before, how many of them are about sadness, how many about dualities, something like that. And for the interest, basically, it evaluates how similar this event, this unseen event to the user, unseen event, is similar to the event that this user has already engaged before. So that represents his interest. So if we are talking about a soccer game, and the user seems like engaged or tweeted everything about soccer before. So if a soccer game happens right now and the user is not aware of, so the potential interest of this user on this event is high. And for the interaction, basically, it talks about the features on Twitter that and how you interact with other people on Twitter, which means which we basically define several features. For example, the number of words you exchange with others, the number of followers the number of replies you have, the number of mentions you have, and last for the influence. Basically, we want to see whether you will get participated in the event. Is how many times that is depend on your friends already in the event, and how many friends that you're following about events. So to this end, we evaluate the number of news agency Twitter accounts that you are following. So if you are following a lot of local news agencies, and if there's an event in Scottsdale, say there's a fire, and you are more likely to get engaged with it, to learn about this event. Because since you are following a lot of news agencies around Scottsdale, so we can infer, or we can predict, oh yeah, sort of you're more likely to engage with it. And also, it depends on the friends that you're following, right? So overall, we obtained around 55 features on Twitter, and to make the prediction. So to conduct the experiment, we only look at the local data, and so basically what we want to do is we want to basically predict the engagement on the on-scene events. And here are the prediction accuracy. So basically we have 55 features, and we use the SVMs, and we want to do it in we have two sets of experiments, the binary and the multi-class. So the binary is trying to predict whether or not you get engaged, and the multi-class is trying to predict the level of the participation or the level of the engagement. Okay, so the last the proposal here, what I mentioned is whether we can do furthermore based on the event detector DEMA and the event predictors Alice, right? So the motivation here is, so the task here, what we want to do is we want to see whether we can do event recognition and the predictions, engagement predictions for the geo-specific events. So why do we want to do that? Because events many times happen locally. And in the meantime, most people have smartphones. You can take a picture, you can send a tweet right away about this event. And if you can do that all the time, that somehow increase or improve your kind of community belongings or civic engagement with your local neighborhood, right? So then the problem is how do we do this event detection for the geo-specific events, and how do we predict the growth and the popularity of the event, and then how do we recommend these events to the potential users? So the proposed solution is that I first want to extend DEMA so that it can handle the events of a particular geolocations. And then we want to develop a way to predict the growth, the popularities, or the potential popularity of the event. Say how many tweets on the event will be, how many kind of how many volumes of the event will be on the tweets, on the Twitter space will be about this event. And then the next is we want to extend Alice, our event engagement predictor. We want to extend that so that we can basically do a kind of event recommendations for the potential users. So at the end, I want to build some kind of global event explorer on Twitter for all the events in the world. So basically, we want to say we can first detect them, then we can rank those events based on their interestness or the predicted interestness or the popularities. And then at last, we want to recommend those events to the potential users. Say, hey, there are some events happening in Paris. You probably will be interested in this. Why don't you take a look? Something like, that's our potential outcome. So here is again the proposed work on the ETLDA, and the extension of the ETLDA and something to handle the events where the transcripts, the textual conjunction is not available, and that's it. And here's the summarization, summary of the contribution so far. So basically, we developed event toolbox called Eventix to support fully automation and examination on the events and its Twitter responses. And Eventix has 4 tools so far: ETLDA, SockSense for event sense making, DEMA for event recognitions, and Alice for event engagement predictions. And here are the publications that I have under this these directions. And I think I'll stop here. Thank you.
So I guess we have time for like maybe a couple of minutes of public questions, and then we will keep him in the lab, and the rest of you can ask more questions afterwards, and probably then we can go into the closed session. Any questions? Yeah.
So as our title is Event Analytics in Social Media, what's your estimation of applying this method? Is this products on YouTube, on Facebook, or other social media websites?
Yes.
Can you repeat the question for John and I?
Okay. Basically, he was asking whether we can apply this event toolbox, Eventix, to other media like YouTube and Facebook. So for YouTube, so YouTube is actually a multimedia, right? So the definition of events in multimedia is quite different from the definition of events on Twitter. So to support and what you are suggesting is that we can use some existing event recognition or event characterization framework developed for multimedia events, and we can incorporate that with the textual comments of the YouTube or Facebook, and we can do a kind of combination, combining existing solutions from the eventics and the existing solutions in the multimedia event analysis. We can do a joint kind of analysis.
So actually, my point is, as all of your work has been done in Twitter,
right?
What you use YouTube and Facebook. Is it proper to use social media in the title, or just use event analytics in Twitter or in Microsoft?
Oh, so I mentioned at I mentioned at the very beginning is that so the event analytics here, that's the title. Probably I should have a subtitle say event analytics on Twitter, but that's a valid point.
It's too critical.
That's a very point. But in my proposal, as well as I think at the very beginning of the presentation, I mentioned that so the full analysis here is we look at a particular platform of Twitter, which is a platform of social media platform, which is Twitter. Given the data that is available to us. So.
Other questions? Okay, if not, then let's, I think the open session is over.